Bismillahirrahmanirrahim. Assalamu alaikum dear students. We are studying the course electromagnetic theory. This is lecture number 3 for class MSc2. I am your instructor Dr. Alam Khan. Today the topic is bound law and conductivity. Consider a material, and if you want to make a current flow through that material, you must push the charges. And if the charge moves through that material, current constituted in that material, and the question arises that how fast they move in that material. The answer is first one, the strength of the push, and second is the nature of the material. Most of the substances at constant temperature, current density is proportional to an electric field E, and this proportionality can be written as J is equal to sigma times E. Here, sigma is the empirical constant known as the conductivity of the medium, and it varies from one material to another. And this equation number 1 is known as Coulomb's law. Regarding equation number 1, this equation is valid for large number of common conducting material known as linear media or the optic media. But in general cases, conductivity is not independent but depends on an electric field E. So J is equal to sigma E, and E is an electric field. Those materials in which conductivity depends on electric field are known as nonlinear or non-optic media. Defining resistivity, resistivity is the reciprocal of conductivity. Its unit is voltmeter per ampere, or known as conductivity as a unit of per ohm per meter, or known as ohm per. Here we are classifying the linear media into two branches. First one is conductor, other one is insulators. Conductor, the special case is metal, or known as the perfect conductor. Here the conductivity is infinite. In insulator, example is dielectrics, known as perfect insulator. Here the conductivity is equal to 0. Regarding the background of the equation number 1, if we want to move the charges by some force, and the force may be chemical, gravitational, or electromagnetic, and here we focus on electromagnetic force, or known as the Lorentz Force, is written as F is equal to Q into E plus V cross P. Current density is defined as J is equal to sigma into small f, where small f is equal to force per unit charge. Using Lorentz Force, we can write this current density equation as J is equal to sigma into E plus V cross V. If the velocity of the charged particle in the material is very small, so we can neglect the second factor, and the remaining factor is J is equal to sigma times. If the charges are at rest, E is equal to 0 inside the conductor. This is the electrostatic case where the current density is equal to 0. And if the charge is going through the material in a perfect conductor, electric field intensity is still 0, but the current density is not equal to 0. This electric field is 0 because the conductivity is infinite. In perfect conductor, less electric field is required to derive the current. Example is electric wires. These electric wires are known as equipotentials. Here we require less electric field to derive the current to the material. On the other hand, resistors are made on poor conducting materials. Let us consider an example. Consider a conducting specimen obeying Ohm's law, a straight wire, uniform cross-section A and a length L, having conductivity sigma, whose ends are made at the constant potential difference V. What current flows in that wire? Now come to the solution. Under these conditions, uniform electric field will exist in the wire, so potential is described as V is equal to integral E dot dl. Because of the geometry of the conductor, electric field must be same at all points along the wire. So equation number 5 reduces as V is equal to E to that. We know that J is equal to sigma times E. Use equation number 6 in that equation. J is equal to sigma V over L. This is known as equation number 7. In the previous lecture, we have established a relation of current in terms of current density. I is equal to integral over S J dot N into dA. If current density is constant throughout the material, then integral can be taken over the surface, and this equation reduces to J into A. Use equation number 7 and equation number 8. Current now becomes of the form I is equal to sigma times A over L. This term sigma A over L can be written as R is equal to L over sigma A, or R is equal to rho L over L. This is known as the resistance of a wire. So from this equation we can infer that I is directly proportional to V, or we can say that V is equal to IR. This is well-known relation of Ohm's law. In general, R depends on current, whereas but linear material R is independent of current. Let us consider another example. Two long coaxial metal cylinders I A and B are separated by a material of conductivity sigma. If they are maintained a potential difference V, what current flows in the length? Now, come toward the solution. As you see in the figure, there is a radii whose radius is A and another cylinder whose radii is B. This is the central axis. S is the distance from the central axis and E is the direction. In the chapter number 1, we have studied the relation of electric field for a linear charge distribution. E is equal to lambda divided by 2 pi epsilon naught into S plus vector. Here the lambda is the charge, the linear charge density is equal to Q over L. Now come toward the equation. I is equal to integral S J dot N into V. Put the value of J over here, sigma times V. Replace E with linear charge distribution, lambda divided by 2 pi epsilon naught into S. S dot N unit vector. After simplification, we get this result, sigma lambda divided by 2 pi epsilon naught S, 2 pi S square. S cuts on up and down, so I is equal to sigma over epsilon naught lambda into S. For the potential difference across the end of the two cylinder, we can write the equation as V is equal to minus integral from B to A E dot dl. The negative sign is due to the fact that we are working in the opposite direction of the electric field. We can take it as another way around, integral from A to B E dot dl. So by using the equation of electric field, we can write it as lambda divided by 2 pi epsilon naught integral A to B 1 over S into dl. After integration, we will get this form of V is equal to lambda divided by 2 pi epsilon naught log of B over. Replacing the value in the current equation, we will get I is equal to 2 pi sigma L divided by log of V over A and B. This term is equal to resistance of the conducting material present between the two cylinders. And we get the result I directly proportional to V. This is the confirmation of the Ohm's law. Now come toward the steady state condition. If the current flow through the material is in steady condition and uniform conductivity, this is the equation known as equation of continuity, and here rho is the charge density, and if the charge density of the material is constant, so the time derivative of constant is equal to 0, hence del dot J is equal to 0. If del dot J is equal to 0, by replacing the value of J as sigma times E, we can infer that E is equal to 0 whether the charges are at rest or moving. Remaining equation is del dot E is equal to 0 is known as the Laplace equation. The result of this equation is that Laplace equation holds within the homogeneous on the material carrying a steady current. Thank you.